This webcast will continue in Worksheet 8F and we'll explain problems 7 and 8. Okay, in problem 7, we have a situation with 4 bobsledders pushing their sled with a constant force. It's initially at rest, but then they move it until it has a speed of 10 meters per second along a flat, 50-meter long icy track. So our system is going to be the sled and the track and the earth. We're not going to include the bobsledders in our system because we're talking about work, and so we want to see that there is work that transfers energy into this system. But let's look at it at position A. The sled is at rest. And at position B, the sled is moving at 10 meters per second. Okay. So at the beginning, there is no gravitational energy because it's on a flat track. The height is not changing. There's no kinetic energy because it's at rest. At position B, there's still no gravitational energy, but now it has kinetic energy because it is moving at 10 meters per second. And so the work that was done on the sled equals the change in the sled's kinetic energy. Okay. It tells me that we can ignore both friction and air resistance, so I didn't put any dissipated energy at position B. Okay, so they're asking me what force the team exerted on the sled. So I think force would be the force by an external agent, right? The bobsledders are external to this system. So the force that they apply times the displacement of the sled while they're applying that force equals the change in kinetic energy, which is half of the mass of the sled times its velocity squared. And here, the thing that I'm going to look for, I'm going to solve for this force. I think I know everything else, but let's make sure. So it says that they applied the force to move the sled along a flat 50-meter track. So that 50 meters is the delta x, the displacement while they were applying the force. The mass of the sled is 235 kilograms. And they're telling me that at position B, at the end, that the sled has a velocity of 10 meters per second, and I have to square that. So the force is going to be half of 235 times 10 squared divided by 50. I'm just solving for the force. Let's see what that is. And I get 235 newtons. By the way this problem worked out, it was pure coincidence that the amount of the force equals the amount of the mass of the sled. That's just the way those numbers worked out. There's no pattern there that you need to make note of. Okay, let's go ahead and look at another one. In problem 8, we have a cannon that is shooting a cannonball straight up in the air. So I'm going to try to draw a cannon here, just a little one. Here's my cannon. And it shoots a ball straight up in the air, and you know eventually the ball will turn around and fall back down. Okay. And it says that the cannon supplies 5,900 newtons of force along the barrel, which is 2 meters long. So while the ball is in this 2-meter long barrel, a force of 5,900 newtons is being applied to it. Once the ball exits the barrel, there's no more force on the ball. it's in free fall. It's going to continue going up because it's going so fast, but it will slow down as it goes up, and eventually it will turn around and fall back down to the ground. So I'm going to assume my system is the cannon ball and the Earth. The cannon is not part of the system because I want to talk about the work that the cannon does. And so the cannon is applying that force to the ball and is pushing the ball upward. So it's transferring energy into the cannon ball. So originally the ball is at rest, and we're just going to say it's on the ground. And then when we look at it again, and I'm going to do this for question B, it says when it first exits the barrel, so it is moving and it's at a height of 2 meters, right? That's where it exits the barrel. So there really is no mechanical energy in this cannonball when we first look at it. It's on the ground, so there's no EG. It's at rest, so there's no kinetic energy. But when I look at it at position B, it's 2 meters higher, so it has, some gravitational energy, and that's supposed to be okay, and it is moving. And so there is kinetic energy. And I'm just going to ignore air resistance because the problem doesn't mention it, and and the cannon is just moving through air. So the work that was done on that cannonball equals the ball's change in gravitational energy plus the change in the ball's kinetic energy. So we can figure out the work, this is part A, because they gave us the external force and the displacement. The work is the F times the displacement. They said the cannon, which is outside our system, right? So the cannon is doing work. The cannon applies a force of 5,900 newtons, and it applies that force all along the barrel, which is 2 meters long. So that 5,900 times the 2 gives me the work, which is 11,800 joules. So that was question A. And now it says, what's the initial velocity of the cannonball when it first exits the barrel? Okay, so I've calculated the work, that's 11,800. The gravitational energy at position B would be mg times the height at that position. The kinetic energy would be half of the mass times the velocity squared. And what they want me to solve for is this velocity. Okay, so let's see if I've got everything else to plug in here. The mass of the cannonball is 3 kilograms. G is 9.8. When it exits the cannon, it's at a height of 2 meters. Okay, so now I have to solve for V. So first I'm going to subtract this term from both sides. And then I'm going to divide both sides by the 1/2 times the 3 kilograms. This is going to give me V squared. So I get that 7,827.467 equals V squared. I need to take the square root of both of those, right? V is going to be the square root of that. So that is the velocity, 88.47 meters per second, just as the cannonball is exiting the cannon. See, I think it asks us another question. What will be the peak height of the cannonball? I'm just going to slide over here to answer part C. That's asking me the peak height. You know, I could draw another energy conservation diagram. At the peak height, the cannon is only, or the cannonball is only going to have gravitational potential energy, right? There is no kinetic energy at the peak because the velocity at the peak for an instant is 0 meters per second. So all the work that was done has at that point gone into changing the gravitational energy of the ball. And so that same amount of work that we calculated in part A equals mgh, and I'm going to be solving for the peak height, right? Okay, and so the 11,800 joules of work equals the 3 kilograms times 9.8 times the height of the peak. And so the height of the peak is 401 meters, 401.36 meters, let's say. Okay.